So our problem for today is to solve an equation 8 to the power x plus 2 to the power x is equal to 130. Well, we immediately see that we can write 8 as 2 cubed and then to the power x plus 2 to the power x is equal to 130. Using the exponential rules, we see that 2 to the power x cubed is equal to 2 cubed then to the power x plus 2 to the power x, which is equal to 130. And then we can introduce the substitution that y is equal to the power x. Then our equation becomes y cubed plus y is equal to 130, which is equivalent to y cubed plus y minus 130 is equal to 0. Now what we have to do is find the roots of this polynomial. For that, we are going to use the following theorem. If a rational number fraction r over s, okay, r has to be an integer and s has to be a natural number, which is not 0, and the grand common denominator between r and s is equal to 1, the root of the polynomial is p a0 plus a1x plus a2x squared plus and so on anx to the power n, where a0 is different than 0, a1 is different than 0, and this polynomial is with integer coefficients. Let's write it like this. So this polynomial has integer coefficients. Well, then s has to divide an and r has to divide a0. Basically, r divides a0 and s divides an. Now, the operating part of this theorem, which we are going to use, states that if an integer r is a root of a polynomial, p, this polynomial, well then r has to divide a0. Now I will show you how to use this theorem for the problem we are given. Basically, we have that a0 is negative 130 in this problem, and 130 we can divide with 2 and we get 65. Then we can divide 65 with 5 and we get 13. 13 is a prime number divided with 1 and 13. Well, this means that our number r is a number in the set of plus or minus 1, plus or minus 2, plus or minus 5, and plus or minus 13. And now we are going to make all combinations of these three numbers, 2, 5, and 13. So we get plus or minus 10, plus or minus 26, and plus or minus 65 for the two combinations. And for the combination of length 3, we get plus or minus 130. Now for the number s, we had that an, which is a3 in our case, and that is equal to 1. We had that s has to divide 1 and s has to be a whole number. Well, that means that s is equal to 1. And that basically means that r over s is equal to r over 1, which is r. And we already have that r belongs in a set of plus or minus 2, 1, 2, plus or minus 5, 13, 10, 26, 65, and 130. So using this theorem, how are we then going to find the roots of our polynomial y cubed plus y minus 130? Well, simply, we have all the candidates in this set which are whole numbers. So all the candidates which are root of this polynomial and our whole numbers are inside this set. So we just have to go through this set for every element and see if that element satisfies this equation. If that element satisfies the equation, it is a root of the polynomial. If it doesn't, then it is not a root. I will test this only for number 1. So basically, if y is equal 1, we have that y cubed plus y minus 130 is equal to negative 128, which is not 0. So y equals 1 is not a root of a polynomial. Now, when we test y is equal 5, we get that 5 cubed plus 5 minus 130 is equal to 125 plus 5 minus 130, and this part is equal to 130, and we finally get that this is equal to 0. So we have one solution of the equation to be y1 is equal to 5. Now our polynomial y cubed plus y minus 130 can be factored by y minus 5, and then we get y squared times y, that is y cubed minus y squared. Y cubed divided by y is y squared times y is y cubed, y squared times minus 5 is minus 5y squared, minus plus y cubed minus y cubed is 0. We are left with 5y squared plus y minus 130. 5y squared divided by y is 5y. 5y times y, 5y squared minus 25y minus plus, we are left with 26y minus 130. And this leaves us with 26y divided by y is 26. So 26 times y, 26y minus 130 minus plus, we are left with 0. So that means that y cubed plus y minus 130 can be written as y minus 5 times y squared plus 5y plus 26. So this is equal to 0 if and only if y minus 5 is equal to 0 or y squared plus 5y plus 26 is equal to 0. Now for this quadratic equation, a is equal to 1, b is 5, and c is 26. I is equal to 1, which is larger than 0. Okay, and we have a discriminant to be b squared minus 4ac, which is equal to 25 minus 4 times 26 times 1, and that is 25 minus 104, and the discriminant is equal to negative 79, which is smaller than 0. Well, that means that this quadratic equation has two complex solutions. It does not have real solutions. We had a substitution that y is equal to the power x, and we are working in real analysis. So these complex solutions are not going to lead us to a real number. That is why we are not going to do anything with them. I'm not even going to try to find them in this video. But in complex analysis, those two solutions are going to lead us to more solutions of the beginning problem. And I will make a video on that later. So 2 to the power x, when we return the substitution, it is equal to 5. And then when we use a definition of a logarithm, we see that x is equal to a logarithm of number 5 to the base of 2. And this is the only solution we have, which is a real number. Thank you for watching this video. Please like, share, subscribe, and leave a comment. I'll see you in the next one.